So that was a question from Muhammad. Any question, any other question? تمام. خلينا نكمل على ما تبقى من chapter 9 اللي هو ببساطة we started to talk about the SCI system that is available in the HCS12 microcontrollers. So last time we saw the details about this module. We saw the block diagram, the operation, how to operate this module. And we looked at the related registers, the control registers, the status registers, and the data registers, which enable us to use the SCI module in this microcontroller. So we discussed that in details last time. So we went through the block diagram of the transmitter, the receiver, and the registers. We talked about the registers, and we covered almost most of the features that we can control through these registers. We did not cover all of them, but we covered most of them. These are the details of the registers. We have two registers related to the baud rate generation in order to specify the baud rate or the communication rate in bits per second. So it is very basic operation to be done here. We have two registers, in total 13 bits, in which we store a value to scale down the E-clock. This is the E-clock in order to achieve certain baud rate. So here we have some examples. We said two examples when the E-clock is 16 megahertz and the E-clock is 24 megahertz. What values should be placed in the baud rate generator registers when the communication rate or the baud rate is in the leftmost column. So these are the values to be stored in the baud rate registers. Here we have the control register number, the SCI control register number 1, where we can turn on the transmitter, turn on the receiver, enable the interrupt, different types of interrupts related to the SCI module. One of them, we said, is the an interrupt that is associated with the reception of one whole word at the receiver, or the interrupt that can be generated when the transmitter data register is empty. So we said we can configure these events to interrupt the microcontroller in this register. This is the second transmission control, the second control register for this module, where we can specify the data formatting or the length of the data, whether it is 8-bit or 9-bit, and specify whether there is a parity and the type of the parity that is used. The status registers, we said there are a set of flags that indicate certain, that gives certain indication about the operation and the status of the transmitter and the receiver. We discussed them in details. Also here we talked only about the BK13 bit, which is basically specifies the size of the break character to be sent out under certain conditions. The data registers, this is very important. We said there is only one data register associated with this module. There is only one address for that data register. So one address, but technically, physically, there are two registers associated with this address, one for the transmitter and one for the receiver. And how does the CPU distinguishes between whether it is addressing the transmitter register or the data or the receiver register, basically through whether it is a write or read operation. Okay. So this was about the data registers. This is the block diagram, detailed block diagram for the transmitter. And we said what are the basic steps that we need in order to use the transmitter. The same thing we said about the receiver. This is the detailed block diagram of the receiver along with all the bits that we saw in the registers, whether these bits are flags or whether these are configuration bits to specify or to enable certain features. We talked about the break characters, how to send a break character and why would a transmitter send out a break character. As we said, this is basically usually, might be usually needed in certain occasions that are approved upon between the transmitter and the receiver. Both the transmitter and the receiver know that a transmission and the reception of break character of 11 zeros or 10 zeros indicate something. They are configured or programmed to understand something or perceive something when they saw a break character. Also, we talked about very quickly about flow control. So basically we said usually in the communication you have a transmitter and a receiver. The transmitter is sending data out at a certain rate and the receiver is supposed to receive the data at the same rate. And this is the basic idea of in-serial communication, whether it is synchronous or asynchronous. However, we said that the receiver might be busy doing something else other than receiving the data from the transmitter. So it might not be able to empty the data register that has the received data as frequent as the data is being received at the same rate by which the data is or finishes the reception of the operation is over. So what will happen? Basically, this is the situation that we call overrun situation, where the transmitter is overrunning the receiver, not because the transmitter is transmitting data at a faster rate, but because the receiver is not emptying the register, the data register, fast enough in order to avoid overwriting the data. Now, in order to prevent this, usually communication systems, they implement some sort or some form of flow control where the transmitter only transmits data when the receiver is ready or when the receiver is available. So this is called flow control. So usually the transmitter will not transmit the data unless the receiver is available, is capable of receiving the data. So two slides basically gives you the idea about flow control. I will not go into details. It is a very big topic. If you are interested, you can go through it. And the protocol that I mentioned at the beginning of this chapter, which is the RS-232 protocol, has special wires or pins that can be used for handshaking or for flow control operation. Okay. So that was what we discussed last time. Let's go over, we have two examples here, or three examples about using the SCI module. So we have here an example where we need to write the sequence of instructions to configure SCI0 module to operate with the following parameters. 9600 baud rate when the E clock is 24 megahertz. Do you see the camera?
Yes, Dr. Shafin.
شايفينها. 96 baud rate when the clock is 24 megahertz. The data format is one start bit, 8 bits for data, and one stop bit. So basically the data is 8-bit format. It's not 9-bit. No interrupts. No interrupts. And address mark wake up. So waking up the receiver is through address mark wake up, not idle line wake up, and we did not cover this in details, but we said that waking up the receiver or bringing the attention of the receiver that it is the one that is addressed and by the transmitter, and it is the one that is supposed to receive the data, can be done by having the receiver monitor the line, and whenever it changes the state from idle to active, it switches its state to active and starts receiving the data, or basically it continuously monitors the line, and when the received data basically is its address, it starts to receive the data and stores it. This is called address mark wake up, address mark wake up. So in this example, we want to use this mechanism to configure the SCI module to use this mechanism. Disable wake up initially. So address markup wake up, address mark wake up, and we need disable wake up initially. Initially, long idle line mode is enabled. Enable transmit and receive. No loop back. Disable parity. So all of these options can be configured by going back to the registers. So I was planning to do that on the board, but that's fine. I will not do it. So similar to what we did when we worked with the phase lock loop, when we worked with the real-time interrupt, when we worked with the A to D converter last time, in order to configure the module under consideration, we just need to go back to the specific registers and set or clear the bits associated with the required feature. So the first thing is basically the baud rate. We are required to use 9600 baud rate when the clock is 24 megahertz. So basically we need to figure out basically what values to store in the baud rate registers, the high register and the low register. And if you look at the answer below, we stored 00. We stored 00 in the high portion of in the upper register, in the most significant register of the baud rate generation register, and 156 decimal, of course, this is decimal, in the lower byte. So we said these two registers together, we specified the scale factor, which is a 13-bit value. So simply you need to do the math. We have here 9600 as a baud rate. Then we have the E clock, which is 24, 10 to the power 6. This value is divided by 16. If you go back, divided by 16, let me go back to show it to you. There is this simple formula. Here you go. 16 times the baud rate register, or the value that is in the baud rate. So you know all the values. So if you do the math, BR will be basically 156, I guess, 156. So let's see if we have this actually in the, if you can do it using the formula or using the table, because the clock is 24 megahertz and we need 9600 baud rate. So basically the value in these registers is 156 decimal. It is 100
divided by 24 ولا 16 كونه انا عندي 24.
لا هي 24 يعني هاي الاي كلوك الاس سي اي موديول كلوك هي الاي كلوك. انا عم بعوض مباشره divided by 16.
تمام دكتور سوري.
Okay, I can take it from the table. It is kind of a lookup table. I can take, it is 156 from here, or I can do the math basically, and I round up. I round the value up. Okay, So this is the important thing to do here is to note here is that we have two separate registers to store this value. And if we go back to the example, to the solution of the example, we have two registers to store the scale factor for the baud rate generation. And this, in order to write to these two registers, we need to use two separate instructions. The first instruction writes 0 to the upper register and 156 to the lower register. Now, if the value is greater than 255, then you need to figure out what is to be stored in the upper register, because you will need the upper register. For example, if the rate is 120, if you did the math and you figured out that BR is 124, for example, how to store this value in these two registers? You need to convert this to binary and then store the lower 8 bits of the binary value in the lower register and the upper 8 bits, or technically they are 5 bits, in the upper register. So 124 is basically 8 zeros. This is just an example, 8 zeros. Then we have bit number 8, bit number 9, and bit number 10. It should be 1. Okay, so this is 00 in hexadecimal, and this is 404 $. So this value should go to the SC0 BDH, and this value should go to the SC0 BDLO. Okay, so this is important. The value to specify the baud rate is stored in two registers, so we need to convert it into 16. The value that we get here, we need to convert it into 16-bit value. Then we store it 8-bit at a time in each of these registers. In this example, we did not do the conversion because the whole value is 156, which is less than the maximum value to be stored in 8 bits. So we can simply take it as is and store it in the low register. And explicitly, the high register is 0. Explicitly, the high register is 0. Now, next, we need to configure the control register number 1, control register number 2, in order to have the specified features. So if we go to, SC0, control register number 1, the value that is stored to this register is 0, 0, 1, 0, 0, which is 4. C is 1, 1, 0, 0. The value stored in SC0 control register number 2 is 0C, so it is 0, 0, 0, 0, and 1, 1, 0, 0. So if you go back to these registers, you should be able to figure out whether these the required features are enabled or disabled. So let's go back, for example, to SCR01. CR1, control register number 1. This is control register number 1. So if you look at the bits that we have here, this is the transmitter interrupt enable. So the example requires no interrupt. So they are all interrupts. The interrupt is disabled. Transmitter transmit complete interrupt enable bit is enabled. Why it is enabled? What were the requirements? No interrupts. So this should be 0 because no interrupts are enabled, right? If we go to the example, excuse me, no interrupts.
دكتور اجس اللي كنا فاتحين عليه يمكن السكند ريجستر كنترول ريجستر نمبر 2.
لا هو رقم 1. This is control register number 2 هذا. Yes, control register number 2. Yes, sorry. had a control register number 1 as few high value. So this is control register number 1. 0 for loops. So the loops option is disabled. This is what happens to the SCI module in wait mode. So this was not specified in the, or it is specified in the features. So it is disabled. The SCI is disabled. RSRC, which is the receiver resource bits, receiver source bit. So this bit is used basically in the single wire operation. So we don't care about it. The M bit is 0 because we are using 8-bit. The wake mechanism, if we go to the wake bit, which is, as we said, we want to use the address mark wake up. So we need to set this bit, which is bit number 3, the wake bit. The ILT bit is also set, which is the idle line type bit. So this is the option that we did not discuss this, but the example requires us to enable this feature. And the parity 0, 0. So the parity is disabled. Parity enable bit is 0, so the parity is disabled. So technically, the parity type is don't care. We don't care whether it is 0 or 1. So we leave it as 0, which is the default value. The parity is disabled, so we don't care about the type of the parity. So this is for control register number 1. Control register number, for control register number 2, we have the upper 4 bits are zeros, which are related to the interrupts. So all these bits are related to the interrupts, though there are no interrupts. The transmitter is enabled, the receiver is enabled. That's why these 2 bits are set. And then we have 0, 0, which is the receiver wake up bit here. So this is the normal receiver wake up bit. And the break bit, we are not sending break bits, so this bit is 0. So this is basically what you need to do. Based on the requirements that you have, the setup for the module or the peripheral device, you just figure out what values to place in the corresponding bits in the special registers associated with the module. So basically 4 simple instructions in assembly: the SCR1 and the CR2 registers. All right, so this is an assembly. You can do the same in C if you want. It is very straightforward. You just in the main program, you write this register name, you set it equal to this value, this register name, set it equal to this value. The same thing for the rest of the registers. So in assembly, in C, you don't have, you just write SC0 BDH equals 0, and that's it. Another example, write a subroutine to output the character in the accumulator A or in accumulator A to SCI 0 channel using polling method. Okay, so we want to take the character that is in register A or accumulator A and send it out. So this is an example on how to transmit data using this module, assuming that you have made the proper setup for your module. Okay, so before you call this subroutine or this, you execute this code to transmit data, you need to set the SCI module properly. So basically, we need, in order to transmit data, if you go back to the last lecture, you basically need to store your data to be transmitted in the data register of the transmitter. And because we are sending, let's say, 8 bits, in this case, without parity, we only need to write data to the low register. If we are sending 9 bits of data, or if whether these 9 bits are raw data or 8 bits plus parity, we need to write the parity bit to the high register, because the high register, the high data register only contains the parity bit. Okay, so basically the subroutine writes the data that is in accumulator A to this register, which is mapped to sub-memory location or sub-memory address. However, before we write the data to this register, we need to make sure that this register is empty. And how to check whether this register is empty? Basically, we go to the transmitter data register empty flag, which is in the status register number 1, and check it with this. As long as this flag or bit is clear, this implies that the register is occupied or this register is full. So we will keep pulling or looping. This is pulling essentially. We are waiting for the register to be empty, and once it is empty, we store the value to be transmitted to that register. Then we have return from subroutine. So as I said, you can call this subroutine from any place in your program in order to transmit one character, given that you have made the proper setup for the module. You have enabled the transmitter in this case, you have disabled interrupts, for example, and so on, all that stuff. You have specified the baud rate and so on. So you may have another subroutine that configures the SCI module according to your needs. The same thing can be done in C. So this is a function in C called put character SCI 0. It writes or it transmits 1 byte or 1 character, which is CX, that is passed as an input argument to the function. And basically here we have an endless loop, which is while that, I'm sorry, it's not an endless loop, a conditional while loop that will keep executing until this condition is false. Once this condition is false, you will exit the loop, and basically you take the character and store it in this register. Now, what is this condition? What is the condition that is being checked? Basically, it is the same that we have here in assembly. We are basically checking the transmitter data register empty flag that is in the SCI status register number 1. And how do we do that? Basically, what is done here, it is ANDing the content of the SCI register with this variable, let's say, or basically it is a constant. What is this? TDRE. It is the name of the flag. But how do you AND 1 bit with 8 bits? It is not ANDing the TDRE bit with the status register bit, because you want to check the TDRE flag that is inside the status register. So what is basically done here? You are ANDing the SCI 0 status register number 1 ANDed with TDRE. What is this TDRE? Basically, it is a mask. It is a mask that is basically 8-bit that is defined in the include file in the C program. Basically, this, I guess it is 80 $80. Let me double check the status register. I guess it is 80. Yes, you see, this is the status register number 1. So basically, to check any flag, you need to isolate the flag out. And how to isolate the flag? You AND the whole register with a mask. So if I want to isolate the TDRE flag, I basically AND it with 10000000. So if after ANDing, I end up with the TDRE flag and zeros. So this is what is done here in this statement, in this C statement. We are ANDing the whole register with this mask. This is a mask. Basically, it is defined in the include file as a constant. So it is replaced by 80. So if the TDRE bit is 0, when you AND it with, in this register, the TDRE bit is 0. When you AND it with 1, then the result of this ANDing operation is 0. Complement, this exclamation mark implies a complement, so this is 1. So while this condition is not true, then you will stay in the while loop. Otherwise, when the condition is true, which is this condition, you will get out. In other words, the TDRE bit is set to indicate that the transmitter bit or the transmitter register is empty. So when the TDRE bit is set, this value, the whole value or the expression evaluates to 1, and when you complement it, it becomes 0, so you exit the loop. Okay, you can think how to, you can try at home or later to use interrupts. What will we need in order to use interrupts to transmit 1 byte? How can we do this using interrupts? This is done using polling, which is basically we are waiting this bit or this flag to be set, then we transmit the byte or store the byte. How can we do the same operation using interrupts? What is the first thing that we need to do? Of course, we need to enable interrupts, right? So we need to enable the interrupt that is associated with this register, with the transmitter data register being empty. So we need to enable the interrupt. Then we need to write a subroutine, the interrupt service routine. And inside the interrupt service routine, what should we write? Should we keep this statement or this line or this instruction?
No.
No, because
This is polling.
This is polling. So we need to remove this instruction and we keep this, right?
Yes.
What does this imply? If this becomes the interrupt service routine, it is no longer a subroutine. It is an interrupt service routine that is stored at a certain location in memory, in the memory, right? Which is the starting address of the interrupt service routine associated with the transmitter interrupt, which is something we talked about in chapter 6. In the table, you will find the list of addresses that are associated with each interrupt source. So the first statement the first instruction is gone. This will be gone. You will not need it. If this subroutine becomes the interrupt service routine of your in your program, you will keep this. And what else? You need to replace this with RTI, what? Because this will become an interrupt service routine. So you need to use the RTI instruction, not the RTS instruction. What else?
Clear the flag.
We need to clear the flag. Yes, we need to clear the transmitter interrupt flag. And how can we clear the interrupt flag in this microcontroller? By simply writing 1 to the flag. By simply writing 1 to the flag. And this is shown or written in the here. If you remember, clearing the flags requires some certain operation. So for the A to D, we needed to write 1 to the flag in order to clear the flag. Here it says clearing the flags require that the status register be read, followed by a read or write to the SCI data register. So clearing the flag here is a bit different than the case for the A to D. We need 2 steps. We need to read the status register, and then we read or write to the SCI data register. In other words, we initiate a new transmission or a new read or receive operation. Okay, so it's kind of confusing. Some maskable interrupts, they don't have flags, such as the IRQ, so you need to clear flags. The RTI and the interrupts related to the phase locked loop, the interrupts related to the A to D, to clear the flags, basically you need to write 1 to the flag. And it is becoming more confusing. When you look to the A to D, we said there are many ways to clear the flags, if you remember. Different approaches to clear the flags. We have the fast clear option also available. Here it is here is another example, which is just the opposite of the previous example, where we write a subroutine to read a character from SCI0 using polling also. So we need to write a subroutine that receives or receive one received byte or one received character from SCI 0, from SCI 0. So the same thing, it is called get character SCI 0, and it is using polling. So basically, to read the received data into accumulator A, we write this instruction. However, we can't read the data until we know that there is a data that has been received. So how can we know that the data has been received? Basically, we need to check the receiver data register full flag. As long as this flag is 0, this implies that no data has been received. So we will keep looping here. Otherwise, we exit the loop and we read the data, then we return. The same thing, we can use interrupts. And if we are using 9-bit mode, whether it is for parity or for data, then we need to read 2 registers, the low register and the high register, in order to read the 9 bits. But from the high register, remember, we need only 1 bit of data, which is the most significant bit in case we are receiving data. Go back to the breakdown of the bits inside the data registers. You will find at the high register, the 9th bit, the 9th received bit is stored as the most significant bit in the high register, while the 9th transmitted bit is stored as the bit number 6 in the data register. So the same thing here is in C, the code in C. Okay. I will leave the rest of the examples for you. They are very simple. They use the functions that we just, and the subroutines we just used. We just show to write more complex programs. For example, here, write a subroutine to output a string pointed to by index register X to SCI0 using polling method. So now we don't want to transmit one character, we want to transmit a string of characters. And it is assumed that this string is null terminated, which means that the last character is null. And what is the null character? It is basically 0, 0, 0 in hexadecimal. So it is 0. The null character in ASCII is 0. So the string is stored in memory, and the address is the starting address of the string is stored in register X. So the string is indexed by register X. So basically, this is the subroutine. We load A, accumulator A, with the character, the first character, and we increment X to point to the next character. So we read the character from memory. Now, if the red character is 0, we branch to done. We branch to done. What does it mean if the loaded value is 0? It is the end of the string. It is the null character. So branch equal, it checks the 0 flag. If the 0 flag is set, then we go here. Otherwise, we continue. What is done next? Basically, jump subroutine, put character SCI0, which is the same subroutine we had on the previous slide. So we just output the character to the, or send the character to the transmitter of the SCI module. Then we keep doing that up to the moment when the loaded character is basically the null character. So this is in assembly. And again, this is assuming that the SCI module has been set up and configured properly before calling this subroutine. The same code here is in C. And if we want to implement the same thing in C, we will assume that the string to be transmitted is stored at some place in memory. And this place is pointed to by a pointer called CX. And we need to use pointers here because we don't know the length of the string, right? We don't know the length of the string. So we keep incrementing this pointer until we reach or we reach the null character in memory at the end of the string. So this is what is done here. While star cx, what does this mean? The value of the memory location pointed to by pointer cx is not null character. Put character sci0, the value of the content of the memory location pointed by cx, then increment cx. Otherwise, you will return, right? Otherwise, we return. So here we need to use pointer because we are working with an array of characters that is that we don't know its size. We don't know the size of this character. Okay. So here are more examples. We have, it is only one example actually. You can go through it. Now, as I said at the beginning of this chapter, this is the SCI, or the serial communication interface, is just one example on the serial communication protocols that are commonly used in real life. There are other examples on serial communication protocols, and technically these protocols are synchronous serial communication protocols. So there is the SPI protocol, which is discussed in detail in chapter 10. It is a synchronous serial communication protocol. And there is the I2C protocol, which is the inter-integrated circuit communication protocol. Each of these protocols, both are synchronous communication protocols, but they differ. They have they differ in many features, such as the use of parity, the use of the definition of voltage levels, what defines one, what defines zero, the number of start bits, the number of stop bits, and all that stuff. So if you are interested, you can go through them in these chapters, chapter 10 and chapter 11. All right, so this is basically what we need from chapter 9. Unfortunately, it seems that we are not going to go back anyway to the university, so we will not have the chance to play around with the boards. I was kind of optimistic that we will at least go after Ramadan to the university, so we'll have maybe 1 week to do something with the board, but today probably you have heard the decision that all exams, the final exams, will be carried out remotely or using e-learning. Anyway, we are just learning something, at least theoretically.
دكتور الله يعطيك العافية.
الله يعافيك يا رب.
بس صار بسيط، يعني أنت شو رأيك في القرار وكيف يعني الوضع بده يكون؟
والله كم الساعة هي؟ 6:28 we have 10 minutes. اوكي، عشان في عندنا كويز احنا، بس انه القرار انا بصراحة مش مبسوط، يعني ومعظم الناس مش مبسوطة، يعني انت يعني قعدت طول الفترة اللي راحت، الفترة الحرجة،